I have a confession to make. My dad loves grass. He literally takes me on car rides just to point out how bad other neighbors' grass is. Love you, Dad. As devs, we don't touch grass enough. In my case, it got so bad, I literally fell out of my chair while coding. I had to pay 70 euros just to have two big guys drag my ass down the street to the ambulance.
Ambulance! Where the ambulance? Why the man body still right there? Ain't supposed to be laying there. Call the damn ambulance!
There was only one logical solution to this problem as an AI engineer. Instead of just walking outside, I spent 5 weeks not leaving my house so I could build a reinforcement learning AI to find an optimal way to touch a grass. Well, and drink coffee and touch water, because I like water. To touch a grass, we need to know where grass is. So how will we do it? Well, we'll do it with the help of OpenStreetMap. So, for example, if we go here and we query features, you can see that's assemble point, artwork, blah, blah, blah. But if we look deep enough, we can see there is grass here. So we'll basically check all the features on the map and which ones are the ones that we are interested, like grass, maybe water. Yeah, 3-2, fountain, so water. And we'll use this to basically navigate. Yeah, here we go, water. So we'll use it to navigate to the map. And one important thing that I didn't know while I was renting house in this area, because that's where I was studying, is that some areas could be green on Google Maps, but they are not nice to visit. For example, yeah, this is all cemetery. So if you find house near it and you think, oh, nice park to walk in, yeah, probably not, so double check. Oh yeah, this is what I started with. And as you can see, it's a complete mess. Why? Because we have the green areas, rectangles, the return way, and the way we choose, if it's the same, it's not clearly visible. We have not enough cafes, if you think about the area, and places where you can buy coffee. So let's see how I upgraded it. Yeah, a bit better. Now we have polygons of the areas that we can walk through, but it's still not super clear to me. So let's do something more. Okay, now we have a map that looks much clearer. We can also see the way back, starting point, which is the green start point. We have nice reward system calculations that we can look into it, number of steps, do we get everything done in time, and so on. How we get it? Well, we specify the tags here. So, for example, for the green, we have leisure, land use, recreation, natural, with woods, and so on. Then we have the water tax and coffee tax. And coffee we can also buy in a restaurant, yeah, or in shops. So that's where we will have coffee. And you will think it's good, but for me it was not good enough. So I have the same map that we have here in Plotly. So for example, if I want to see without all this gibberish, just a return road, I can see it basically here. I can play with it, see the gray starting point, green area, the rewards that I get for a green space, and so on. And now if I make a road visible, we will see the walking road and so on. You can see the available shops to drink coffee, and then visited shops with a coffee cup as our indication. So you can see there is like 3 coffee shops visited, so we get a reward for 3 coffee shops. You can see their names and so on and so on. So, of course, it wasn't easy to put it into TensorFlow. It's actually not allowed. And I decided to use TensorFlow to track experiments. So I needed to play around to figure it out. So I needed to fix some issue. And the issue was that for Plotly to save image into PNG so I can pass it into TensorFlow, I need to get Chrome. And well, if you know about security, you don't like Chrome because Google will get all your data and try to sniff it. And I find some Stack Overflow definitions and so on and spend quite some time. But actually what I do is I just reduce the Plotly version to the one that don't implement this, and I save it into UV, so if anybody wants to fix it, you can just look at my version in the file that I will upload to GitHub like everything else later. Now we'll go through how I created the reinforcement learning environment. I will try to explain it quickly and easily. I created this README file and proofread it by help of AI, so I have better visualizations. I actually try Google, ChatGPT, Grok to visualize some parts of this code, but they perform poorly or make wrong pictures, so I'll do it with that. So basically, imagine you go on a walk and we want 60 minutes of walk and we want to see green spaces, yeah, because from psychology, humans evolve too fast, and when we are going into nature, we actually activate hormones for alertness because we are looking out for dangers like a saber-toothed tiger trying to kill us. So this still works. So we want to look for green spaces, water, because I like personally walking through water, and also typically because of humidity, it's kind of cooler in summers. And we want to also pass near cafes. So we want, need power as developers for coding and stuff, so we need coffee. We also want to explore new paths, so we don't want to work in circles or doing the same paths each day, which typically humans do when they go on a walk. So then the plan will look like this. How the AI will learn that? Well, typically we have environment. So then in our case will be the map. We have the observation space. So what the agent will see. And we have states where we reward it for good and bad actions. We penalize it. And the agent will look at the observation and the rewards per each step. And at the end of each episode. So episode is like a simulation. So one simulation will finish with either success over time or failure. So that's the more or less explanation of what's going on. Now, in our observation space, we will have 7 values, so 7 states. So first is the target duration of our walk that we will set up. For my tests, I experiment with quite a few of them, but I stick to 60 minutes because for 30, there's not many nodes on the map to explore. So then we have total journey time. I actually started with just the current duration without counting the return trip, and I put it separately, but I think, it's not very wise, and the algorithm seems to perform better and get better results faster when it has one value, because then it's clearly explained also to humans. I basically, when we do add some road, I also calculate the return road with shortest path, and that will be the total journey time. Then green and water coverage. Basically, I added area around nodes when we walk, which simulates basically what we see around typically. And this area will be adding everything we see around as, like, for example, green and water areas, and further rewarding our agent for seeing them. Then we have coffee counts, so how many coffees we drink during the trip, so refill ourselves. Time since last coffee. This is actually not that I think important, but I added it because we can't drink too many coffees typically. We drink one and then we have some rest. And if I don't put this limitation, then the agent could find out that if it goes to an area where there's a lot of coffee shops, he can drink coffee all the time and then ignore all the penalties. And we don't want that. So basically he will cheat. And then we have route uniqueness. So if we cover the same route all the time, we'll not get points here. So this is the breakdown of the values also. So more visual one. And now we'll go to the detailed explanation. So basically we have target duration that I explained before. So I set it to 60 minutes. And the agent must plan the route, so it will match it. We have total journey time. So as I explained, walk and return time. Then the green coverage. So what percentage of my road is near green spaces? So here we can visualize it. We walk through road, which you can imagine as a sphere or a rectangle. And if it matches with the area of the park or water, we'll get additional rewards for that. And then the coffee can. So as I explained, we, for example, can get it every 10 minutes if we find the coffee shop around. If we don't find it, then we can visit it. And you can also visit all a few of them in the same time. So we need a break, basically. So our poor developer heart don't pop out. Now the uniqueness. So basically the full map perform on edges. So the formula is we divide unique edges by total edges. So we will basically see if we don't travel in circles and visit the same edges all the time. Now the action space, so that's a very important one. So that's basically what agent can perform in the environment. So in my case, I choose only 2 actions. So the action 0 is that we remove points if we are over time. So we basically pop nodes from the top of the road that we created already. And this will shorten the duration, total length of the trip, basically. And add point is we just choose random point along the map and formalize route to it, which is shortest through nodes, and then calculate the distance and go there, basically. The important part, which I actually struggled for quite some time to figure out, is that depending on how big map you choose, I choose this point with like closest proximity, because if I choose that the random point could need to be over 800 meters from the starting point, then for the agent it will be very hard to find the roads that will then basically finish on the set duration. So I struggle with it quite some time. We can look into TensorFlow later, how I visualize it. So basically, if our target is 60 and there is 75 minutes, then we'll cut it. And we'll cut it in a way that we still have shortest road to come back, basically. And then, as I explained at point, and we also have penalties. So for example, we have small penalty to discourage from constantly doing steps like 0, because we can, for example, use it in the beginning. Basically, the agent could cheat. So basically, I was adding points for visiting nodes, but then it figured out that actually I don't 0 for visiting the same ones. So he was popping out the nodes from the top and then getting points for the same role that he already have. So if he spawned this behavior, he could amass a lot of rewards. Now the reward system, so how it works. So in a step, we have quality improvement, which is the weight penalty if we get it. So basically step reward is quality improvement, which is of quality score. So green, water score, coffee score, and uniqueness road. And we add overtime penalty if we are overtime, or terminal bonus penalty if episode ends. And then also there is success one. And here we have an example of broken reward. So we see some coverage and then we get the sum. The quite important part when designing reward is that I define like maximum reward, for example, for green coverage, but the map could not provide enough green space to ever achieve that. So in practice, you get around 70% in best cases and so on. And then we get number of steps in an episode. So in the simulation run, so the current score minus the previous score is the step reward. So this guide the agent during each step, so he knows if he improves or not, which is important because if we give big rewards at the end of episodes, we don't know which actions actually were most contributing to it. Then we can have overtime penalty. So if we stay over time, we'll start getting penalty. So the agent will basically get a signal that it's time to finish and he's doing something wrong. And then if we have success, which I defined as 5 minutes, and it's absolute. So if we define 60 minutes, then we can finish in less than 65, higher than 55. I started with like 2 minutes, but it's quite hard depending on the map to find routes like this and nodes. So I increased it to 5 minutes, which I think is pretty realistic. Then if we are over time, so over this 5 minutes window that we have over 60, then we are losing. And then if we go over steps, we get minus 0.2. This was mainly to prevent cheating that I will show maybe now. So basically, I model it's some old runs, so not everything is perfect here. And that's how it looked at the beginning. So we get some road, we go over duration, so we don't succeed, we have minus reward and so on. But because my rewards were not best, and also the agent have kind of unlimited number of steps, it figured out at some point that it will just add nodes, delete them, add nodes and delete them infinitely, basically till it go to maximum number of steps available. And as you can see, it amass a lot of reward for it. So that's what typical reinforcement learning do, is it finds all ways to cheat if you don't design your environment correctly. And now we can look at the life cycle of the simulation that I explained. So we do steps. Here I define max 15. And then at the end, we either get success, we get overtime, or we get truncate if we run out of steps. So agent start the multiple steps. There's termination, there is another run, and by the reward, we basically can see if the agent is learning something or not. This is a nice visualization of the conditions. In my case, if remaining time is less than -5, so basically when we are overtime, then if we are in the duration of error, we qualify it as success. And if we go over 50 steps, we are getting the minus reward for this. Actually, I should technically make it higher, but I don't see agent finding this cheat way again. Maybe I will make another longer run to see if I don't need to increase it. Okay, guys, now we'll dive into the graphs and how agent was cheating on our reward before that I mentioned. As we can see here, duration 0, beautiful yellow on white background, which is reward. It's 900. We see we do over 101 steps and nothing is marked and so on, and we have a big reward. So what happens? So actually our agent learned how to do reward hacking. It discovered that it could farm points by adding and removing the rows over and over again to MS points till basically it achieved the limit of steps. Now I use TensorBoard because it's recommended for the Gymnasium and the custom environment I make to track all these results. So here I marked everything and we'll go through it very quickly. If you want more details, let me know or subscribe so I know that you guys want to have a more insight into all of this. I try to do it quite broad for everybody to have some value out of it. Okay, so we can see a few things here. So this run, which I name it pink because I'm a man and I don't recognize many colors, will have pink, red, and blue. So the pink is the cheating run. I choose it because it's interesting. We can see, maybe starting from the top, that we have sudden dip and in the adding points, and then in removing points we have big increase, which is different for these two runs. I only put them here so you can see the difference more clearly, and I will talk about them later. So now we have how many times we visit cafe and we see sudden dip. Then we see that the reward also increase around this dip. It's 1,200 steps. Maybe this I can show on a bigger one. Then if we go to the steps, we also see that the steps suddenly start increasing. The steps are how many actions were performed by the agent. Success rate was not tracked here because I didn't add it to the TensorBoard in this run, but it was much lower than any of this anyway. And we see that the water coverage also goes down. It's typically low because there's not much water on the map. If you put a beach or near sea region, you will get much more, basically. This was not tracked in these runs, but in other runs. And then we see also the green coverage, which also go down, and so on. So now we'll look at the training, and here you can see much more happening. So to explain it quickly, I will use the student as an example to make a clear explanation of what's happening here. But if you see the good runs and bad runs, then it's quite clear that something wrong is going up there. So now, if we look, we have the approximate Kullback Leibler divergence, which is basically the speedometer. So it measures how much the student strategy changed between the last session and the new one. So basically, if it goes up, the agent is making massive radical changes to the playstyle. So our student is an agent, so the RF agent. And if it goes down, then the student is making tiny fine-tuning adjustments. So as we can see, we have high peak, and then the students, it goes down, which basically means that we change the strategy too fast in this run, which is the cheating run. And this happens around basically the run when it discovers how it can cheat to amass a big reward. Now, if we look at the clip fraction, so I never mentioned it before, but it's important. I use PPO, but I use basic PPO. It's typically used algorithm for reinforcement learning. So if you want to know more, check some internet videos. If they're not good explained enough, I can work on explaining it visually more. And also, then I'll understand it better because I'm not an expert. So basically, it tells us to don't change the mind too much at once. It shows how often the algorithm had to step in and say, stop, we do too much changes. So if it goes up, the model is being very aggressive and the safe error rails kicks in. And if we see changing here, it basically means that the learning rate could be too high and so on. The clip range is stable, I think, so we don't really need to go deep into it, but it defines the boundary of this seatbelt that was mentioned before. Now, entropy loss. So the entropy loss is the measure how random or uncentered the student agent is. So basically, if we see negative number or it moves towards 0, it means that it becomes less curious and it's stuck in their ways. So basically the agent gets stuck in the cheating here and it just wants more rewards and so on, and it don't try anything. We can also see it, here that we don't visit as many cafes and so on, even though we can get some rewards out of it. The agent just ignore it because the reward from other things are so big. Now, explained variance. So that defines Does the student understand when they got a high score, or was it just luck? So we can see, for example, here that the student for the cheating one didn't really understand why it get all of these things, so it's fluctuating and so on. And in other cases, it's steadily, basically after some breakthrough grows and so on. Now the learning rate was the same for all runs, so nothing very interesting here. All right, let's look at the value loss. So to understand this, remember that AI agent is a student. So at every single step of the walk, the student is trying to predict what its final grade or reward will be. And the value loss defines how much the student's guess differs from the actual result. So when we see this loss drop, it tells us the student is finally learning to accurately value its progress throughout the episode. But look at the numbers here. The value loss is hitting really high numbers compared to the last runs. So that tells you I changed something because it was not working. So this is a problem in deep learning, that big numbers are our enemy, because when the rewards are massive and unscaled, the neural network has to make giant leaps in its math to try to predict them. And this creates aggressive gradients that shock the model rather than teaching kids. So it's like a teacher screaming the answer loud in class while bursting K-pop music while you are writing exam, and you need to make sense of it and try to think, basically. So this is also where the cheating behavior show up, because the agent found a way to farm infinite points and the rewards became so inflated that the value function can't keep up. Basically, the student is overwhelmed by the number of goodies that it gets and it's trying to guess. So to fix this, I implement few layers of protection. First, I implemented special calculations. So basically now we have differential improvement. What it means? It means that each time we update the reward, we subtract from the current score, so the all score for these rewards that you can see here, the previous score, and then I clip it also to be sure that the number don't get too big. So what it do is that if the agent tries to farm points by undoing and redoing moves, the differential math makes the net reward 0. So this prevents the value loss from exploding and keeping the training stable, and it forces the agent to move forward. If it's adding value, it gets paid. If it don't add value, it isn't getting paid. Now, if I look at the config, I also minimize these rewards, because I was putting really big numbers like 500 and so on, and it was too big for this kind of training. They probably need still optimization, because typically creating good reward system for your environment is the hardest step. And if we look at the train, I also implement the vec normalize. So what it do, you can think of it as translator. So it takes these giant numbers and squash them into smaller ones, so the neural network can actually digest them. Now, what is the policy gradient? This is basically our game plan. So if the agent finds park, cafe, green spaces, and so on, it gets rewarded. And the policy gradient loss kind of pushes the agent to take that action more often in the future. So typically it stays quite slow and it spikes gradually. But we can see that in the cheating one, it spikes suddenly, which means the agent was panicking and drastically trying to change its strategies to get reward. But it was confused why it's getting so much of it. Okay, so with the magic of video editing, now I cut to just the two last graphs to show you something that I struggled quite a lot, that I also mentioned before. So as we can see, I added success rate. So this basically tells us what is the percentage of success compared to anything else in our runs. And the success is defined by getting the correct duration with the absolute error of 5. So as we can see, there's big dip in these two runs. And now why it happens? So actually we have in at point, we have a range, so a distance of where the node will be choose from. And before it was 0.08, which is like 800 meters. So actually for the duration of 60 minutes, that was 2 big steps. So there were not many nodes combination that will make the agent succeed in fitting exactly in this tight value. So that's why I modified to a lower step, which is 300, 0.03. And this allows us to get much closer durations. Yeah, and if I lower it, it will also be longer, but then the agent will make more steps and the learning will take more and more time. And I use my CPU to full, I make training in parallel and so on. So this fixed the success rate, increase it. But then if we decrease the amount of road we can add in one step, then I needed to increase the number of steps. So because the steps at the beginning are much higher than before, yeah, you can see it was around 20 and here it was 8 because we could cover much higher distance using action 1. So I increase the number of steps. Yeah. So I increase the value of these steps from 30 to 50, so the agent have more time to actually find the perfect duration. And if you put more of it, then there is higher chance. And then, for example, you can lower the distance again and more. The agent will fit the distance much higher, but then you will need to train it a lot. And I didn't have time to train it fully, either resources, and I spent few nights listening to my laptop making weird noises. So yeah, I decided that this is good enough. Sometimes you need to do in engineering. And also the interesting part, this is all the runs. You can also check here all the images from the runs with the roads. Unfortunately, I don't know how to make it in TensorFlow visible, because as you can see, the picture is so big that it's not very clearly visible. But so now the question is, we train something and we want to know how it performs. So we can do two types of tests. I vibe coded this because I really spent a lot of time making this video and on writing all of this code. So I create evaluate, which I will deep into more probably in the future or rewrite it myself. But for now, we use this. So we make it run, for example, for our Rust run, because there's model saved here in these old files. You can see there are HTML runs, there is runs trainings and model in PKL and so on. So in the config of plots and basically everything, so we can also see how I train the model, how much CPU percentage I use for parallel runs. I put it quite low because the saving out pictures actually take quite some of memory, so maybe it's not fully optimized, and my PC crashed at least 20 or more times. So that's what I find out work for me. So I do 2 evaluations on pretty low number of episodes, but we can see. So here I put the same starting point. As we can see, we get success, we get good rewards. And different roads. We touch a bit of grass, we drink some coffee, so pretty good. The road is maybe not best, but it's different each time, so I guess that's kind of achieved. I will run more training when I get better resources, because it will be soon, guys, so we can do more crazy things, but I'm using 3 years old laptop. So yeah, but this is not a good idea, because we check it on something that was trained, so like, yeah, it's pretty easy. So I change it with the start location parameter, so if I add a bit different location from training, so the point is a bit different, but it's still the same map. So here we can see now that some of these runs don't succeed and we get minus reward, and we just change the point a bit. Like if you look at it, here is the point that we have, basically what we trained for, and here we change it like literally a bit on the other side, basically from here to here, and this already decreased the performance. So that means that we need much more training to generalize better. And if we look at the graph, we can see that in the training we have a bit of fluctuations, for example, in the reward. Now let's take one run. Yeah, so we can see that during the training, the moving average of the reward was kind of oscillating, which means it's still not fully optimized, but I just didn't have resources. Like in the grand scheme of things, if you run many runs, it will like be increasing till you achieve plateau, and then we can't get more gains basically. And maybe few examples from the final run. So at the beginning, we see we have some success, sometimes some failures, and the routes change, and so on and so on. I actually wanted this video to be much more visual, but I spent so much time on just making something so simple as this that goes beyond me. And then if we look, we have much more successes. We still have sometimes overtime, yeah, but the success rate is quite high. We have different routes and so on. Here we have overtime. We drink some coffee and so on. We can also look at the episode 2010 in my interactive map. So now if we look at the map, we can make it clearer. So you see where the coffee got visited, and we get the bonus points. Actually, it shows 4, but it shows opportunities here to drink coffee, and here we see that it visited 3 of them. So it's not perfectly cleared, but yeah, try my best. We have the return route. So we finish here. It was 7 minutes to return. And then we like this very weird route all around parks, but that basically means that because how it's calculated is the area around, that it was getting a lot of reward from the green area, which you can see here. And the water is pretty far, so it's pretty hard to find all around this. Okay, so that concludes my video. I spent quite some time working on it, much more than I expected. See you in the next one.